G'day everyone. In this video, we're going to be examining this series or family of definite integrals, which is the integral from 0 to pi over 2 of 1 over sine to the power of 2n of x plus cos to the power of 2n of x, where n is a natural number. So, believe it or not, this can actually be resolved in a very simple mechanics, just with a couple of basic substitutions and usage of trigonometric identities. The first thing that we're going to do in this is we see here that we've got 2 to the power of n, to the power of 2n, sorry. We've got to the power of 2n as well. So what I'm going to do is I'm going to bracket off the to the power of 2 component. So I'm going to employ the indices laws and just separate it out. So we see here 1 over sine to the power of 2n of x plus cos to the 2n of x is equal to sine squared to the power of n plus cos squared to the power of n. Now, the reason why I'm going to do that is because I'm now going to employ, what are they called, the double angle formulas associated with both sine and cos in order to be able to reduce this from a sine squared down to a cos term. And so these are well-known trigonometric identities. Generally, they're in the form of cos 2x equals, and often they're presented for both sine and cos. However, the nice thing is that with the cos 2x form, it can account for both sine squared and cos squared. And the most important thing about it here is that it takes it from a squared term, which is what we have here, and it reduces it down to cos of something, but only raised to the power of 1. So in case you're wondering why I've made that step, that is the reason why. So we're just going to substitute that in the next step. So again, what we have here, which is what we had here before, we should have really ignored that step. So you see here, what I've done is I've replaced the sine squared component with this 1 minus cos of 2x over 2, and then the cos squared component, I've replaced it with 1 plus cos 2x over 2, which is what we have here. Sorry about that, that's my phone. Okay, so you'll see on the next step, all I've done here is we have a common divisor, a common denominator, I should say, sorry, not divisor, of 2 to the power of n. So I've just brought that out the front. And you'll see here what's left is just the top term, the numerator term here, 1 minus cos of 2x to the power of n. And then on this component here, it's just 1 plus cos of 2x to the power of n. So again, very simple step. Division by a fraction is obviously just the same as multiplication by its inverse. So that becomes 2 to the n over 1, or 2 to the n. As it's a constant, we've just bringing out the front, and then we have what we have here. So the next step here is, instead of having this as a 2x, I just want to reduce it down to a cos of u, or a cos of some other variable. In this case, I've let it equal u. The reason why I'm doing that, once again, is just to simplify the expression that we're dealing with. So we could really leave it at that and proceed on with the method that I'm going to take following that. Excuse me for 1 second. I've still got a flu. But I know through experience that it's much easier if I reduce it down. And because we've got cos of 2x again, it's going to reduce it down in both cases to the same form. So it's just, yeah, as I said, a means of simplification. Okay, so we let u equal 2x, which means du dx is just equal to 2. Rearranging this into the form of dx equals, we just have 1/2 du, so just multiplying the dx up and then dividing by a half. And then in terms of changing the bounds, at the lower bound where x is equal to 0, we have u is equal to 2 times x, or 2 times 0, which is just 0. For the upper bound, pi over 2, x is equal to pi over 2. Remember, u is equal to 2x, so 2 times pi over 2. The 2 here cancels out with the denominator here, and we're just left with pi. And so therefore, this original integral, which is what we have here, gets replaced with the 2 to the n, remains unchanged. We see the bounds, they go from, as we had before, 0 to pi over 2, gets replaced with 0 and pi, which is what we have here. 1 over, and you'll see that, as I said from before, we've replaced 2x with u, so we have 1 minus cos of u to the power of n, plus, 1 plus cos of u to the power of n. And then dx here, as we went through just before, that gets replaced with 1/2 du. So this 1/2, I'm going to bring out the front and see we've got a common factor here of 2. So this is just using our indices laws, 2 to the power of n minus 1. The integral from 0 to pi of 1 over 1 minus cos of u to the n plus 1 plus cos of u to the power of n. So this next step here, and just so you know in case why I've taken the next step, whenever we've got rational functions, so functions that involve fractions of trigonometric expressions that we want to integrate, this is not an absolute way. Well, actually, it is an absolute way of being able to approach it. You can employ what's known as, and I'm sure I'm mispronouncing it, but it's commonly attributed to Weierstrass. It's often, yeah, WEIR, or I forget what it is. But it's also referred to as the tangent half angle substitution. And it's a very, very common one. And we see it's, we let T, I'll have a link to the corresponding Wikipedia article for it. But if we let T in this case equal tan of U over 2, then by just applying some trigonometric identities, we find that du is equal to 2 over 1 plus t squared dt. And cos of u becomes 1 minus t squared over 1 plus t squared. Now I know if you're not used to that, that's a lot of information. I've done a lot of steps in one. I could do a full separate video just on this. So as I said, I will provide a link and I recommend that you go to there if you're not familiar with it. If you would like to see a video where I go through the derivation of these steps, by all means, please comment or send me a direct message and I'll happily put together a video on it, because it's definitely, if you're doing any integrals that involve rational trigonometric functions, it's something that you definitely want to have. It is without a doubt my go-to. Sometimes I will look at rational expressions and I will see other sort of patterns that emerge from it where I can employ a simpler approach, but this is a fail-safe, it will always work method. Okay, so we know how to replace cos of u. We know how to replace our du term. Obviously what remains is replacing the bounds. So remember, we're letting t equal tan of u over 2. So when u is equal to 0, we have tan of 0 over 2, which is just tan of 0, which equals 0. When x equals pi, we have u is equal to tan of pi over 2. Tan of pi over 2 is actually discontinuous at pi over 2, but it has a limit and it approaches positive infinity. So these bounds go from 0 to pi and get replaced with 0 to infinity. Cos of u gets replaced with this term here, and our du gets replaced with this. So again, so what we're doing in this case here, is that we're taking a rational function of trigonometric terms and we're going to replace it with an algebraic term of polynomials, and they are much, much easier to integrate. Okay, so there's a few steps here. So in, which is equal to this expression as we had here, gets replaced with this 2 to the n minus 1, obviously remains unchanged. Our integral bound, again with my phone, gets replaced from 0 to pi to 0 to infinity. 1 over 1 minus cos of u, so 1 minus this term here, 1 minus t squared over 1 plus t squared to the power of n, plus, and then here we've got 1 plus cos of u, which is 1 plus 1 minus t squared over 1 plus 1 minus t squared, over 1 plus t squared to the power of n. Our du term gets replaced with 2 over 1 plus t squared dt. So just doing these there's multiple steps that I've done. I've actually separated it out into multiple steps because there's a lot of algebra going on here, but doing it bit by bit. If we draw this 2 out the front here, we see just with our indices laws, this is 2 to the n minus 1 plus 1, which just goes back to being 2 to the power of n. The integral from 0 to infinity, and then what I've done in this step here is just put this over a common denominator. So we have 1 plus t squared minus 1 minus t squared over 1 plus t squared here. And then for the second term here, this becomes 1 plus t squared plus 1 minus t squared over 1 plus t squared, and we still have this term 1 over 1 plus t squared dt here. Okay, so moving it on to the next one here, just simplifying this out. 1 minus t squared minus 1 minus t squared, well, the 1's cancel out, and this t squared minus t squared becomes plus t squared, and so we've got 2t squared over 1 plus t squared to the power of n. For the second one here, 1 plus t squared plus 1 minus t squared, we can see here 1 plus 1 becomes 2, but the t plus minus t squared, the t squareds cancel out, and we're just left with 2 here. So that's what we've got on the next step. Now you'll see here on the numerator for these fractions on the denominator of the integrand, we have a common factor of 2 to the power of n if we expand out our indices law. So if we bring that out the front, well actually my apologies, we've got more than that. We've got 2 to the power of n and 1 plus t squared to the power of n. You'll see that that is common across both of them. So drawing that out the front, we have 2 to the power of n, 1 over 1 plus t squared to the power of n, and then what's left over is what we have within here. So t to the power of 2 times by n. So that's where the t to the 2n comes from. And then over here, we've just got a 1 because we've drawn the whole thing out. So we just have t to the power of 2n plus 1. And then again, we still have this term from before, 1 over 1 plus t squared dt. So simplifying things down, We see here what we have here with this 1 over 1 plus t squared to the power of n. Obviously, because we're dividing by a fraction, that's the same as multiplying by its inverse. So we would then have 1 plus t squared to the power of n on the numerator. But you'll see here we've got the minus 1. So that minus 1 comes from the fact that we've got a division of 1 plus t squared. So again, in multiple steps here, 1 plus t squared to the power of n, that gets flipped up to the top, but then it becomes minus 1 because of this term here. What we have remaining on the denominator is just what's left over, t to the power of 2n plus 1. And you'll see here this 2 to the power of n, which is just a constant. If we bring that out the front, it just cancels out with the term that's already there. Okay, so now we've got this expression to integrate, and believe it or not, that is much, much simpler to integrate, and it actually has a very simple form.